Okay, since last class we spent the whole time doing problems, I'll answer problem questions on Friday. Um, if you have any problem questions, feel free to email me or whatever, or come to office hours tomorrow. But I'm gonna just try to get a ways into the new material, so I have some problems to give you. So we've been doing particle kinetics, and now we're moving to rigid body kinetics, which we're going to spend a lot more of this class on. Um, and before we do that, so in deriving stuff for rigid bodies, you first start by thinking about collections of particles, and then eventually you make it infinite collections of particles that have rigid relationships. But what happens if you have a collection of particles that aren't connected to each other rigidly? So think of this as like an intermediate step, and we're not going to spend much time on this, but I do want you to remember this one thing. And I've grown fond of calling this pudding dynamics. It's like lots of particles, but they don't have any particular relationship to each other, you know? So these are collections of particles that aren't rigidly connected. So that's pudding dynamics. What can we say about that? So if you just have a bunch of particles, a bunch of bowling balls out in space, or a bowl of pudding or whatever, what can you say? You might ask whether there's anything useful you can say about the dynamics. So can you say anything useful about it? And the answer is there's one very useful thing that you can say about it. So Newton's second law, when you extend it to just random collections of particles, says the sum of the external forces. So like when I write Newton's second law, I always just write the net force, right? And the net force is all the forces. But, we've talked about the fact that you don't have to worry about the internal forces because they always come in Newton's third law pairs. Okay, so here this is going to be an important thing. So add up all the external forces. That means that if these bowling balls in space collide with each other, you don't have to worry about that. Okay? And that's equal to the total mass of the system times the acceleration of the center of mass of the system. And this is like shockingly useful. Okay? So, like, for example, say you have 50 1 kilogram balls in space. and you apply a 20 Newton force, let's say up. I don't know what up means in outer space, but 20 Newton force up to one of the balls. What's the acceleration vector of the system's center of mass? I mean, like when you think about it that way, it's kind of crazy that we can calculate anything here. I mean, I didn't even tell you if these balls are within, light years of each other. You know what I mean? They could be next to each other where that force makes one smack into the other ones, or they could be totally separate from each other. And in either case, Newton's second law says that this force, so I'm going to just call it 0, 20, that's the upward force of 20 newtons, is equal to the total mass of the system times the acceleration vector of the system's center of mass. And so that says that the acceleration of the center of mass is equal to 0 for x and 0.4 for y. And that's true whether those balls make contact with each other or whether they don't make contact with each other. Okay? So that's amazing, Can you say anything else about it? Well, you can say, so this is the first time that rotational stuff, moment-related stuff is going to come into it. You can say that, so I'm going to call this rotational Newton's second law, rotational Newton's second law, and I'll just always abbreviate that Rn2L. And what you can say is, if you take all the, I don't know how to abbreviate this, but all the external moments about some point A, and we're adding them all up. Okay, so it's moments produced by external forces about a point A, and then add them up for all the different particles. This is equal to the time derivative of the angular momentum about that point A. And to calculate that, that would be like the sum of all the so the row vectors, which we haven't even talked about, I guess I'm just writing this to show that it's kind of like this complicated thing, times the mass of the particle, times the velocity of the particle. We're doing this particle by particle, so each one of these, we're doing this for I equals 1 to n, how many particles you have. And then you're taking the time derivative of that. Okay, so for Newton's second law, you have this really useful thing where you can talk about the motion of the center of mass. This, only in very special cases is this useful. This is not usually useful. Okay, so something, you can tell something about it, but not too much. Okay. Oh, by the way, the Newton's second law thing, that says, like, you can use that in a lot of cases. I'm standing up like I'm going to actually do this jump, but I'm not because my back hurts. But if I jump up into the air as hard as I can, okay, like say that I want to get my center of mass as high as possible, okay, what would you think is the best way for me to get my center of mass as high as possible once my feet leave the ground? You might think, oh, I'm going to lift my legs up. I'm going to lift my arms up, get the center of mass of all of those things as high as possible. But that Newton's second law thing says no, you can't do anything to control it. Once you leave the ground and you have the only external force on your system of particles is the weight acting down, anything else you do is just internal forces and they don't have any effect on the acceleration of the center of mass, okay? So, like there's really useful things you can say about the motion of the center of mass based on that. I think there's one homework problem you have to do like that, and it's very similar to like the bowling ball in space question. Okay, so now what if the collection of particles is organized into a rigid body? Oh, actually, I left something off. It doesn't really matter because we're not going to use this. But will you put a little note in here because I wouldn't be able to sleep tonight if I had left this off. So I said that the moments. So you're calculating these moments and this angular momentum about this point A. That doesn't work for any A. A has to be either the center of mass or a fixed point. Okay, so now what if the collection of particles is organized into a rigid body?
Would the fixed point be something specific on our coordinate system or our body attached?
Okay, yeah, good question. So we'll talk about this more with rigid bodies, but we still have to have inertial coordinate systems. And once you choose your inertial coordinate system, that fixed point on the body has to be fixed in your inertial coordinate system. So if our coordinate, the easiest case is, usually our coordinate system is going to be on the ground, and then it just has to be like a pin joint or a ball and socket joint connecting the body to the ground. Okay. Now what if the collection of particles is organized into a rigid body? Then there are two things we can say, and this is so much of the class is going to depend on this stuff. So first we can say Newton's second law, that if you add up all the forces on the rigid body, and again, these are just external forces, but I'm going to leave it out here because we're just sort of used to thinking of it that way. This is equal to the mass of the rigid body times the acceleration of the center of mass. And then we also have rotational Newton's second law. And that says that if you add up all the moments about this point A, it's equal to the moment of inertia about that point A times the angular acceleration vector. And just like with pudding dynamics, you can't choose your about point anywhere. So remember, for all of you who've taken statics, I think I mentioned this in statics, in passing, is like, statics is nice because a lot of the difficulty of the math comes from the motion of the bodies. And so you get to learn about free body diagrams and stuff without worrying about the motion, and then you add it in dynamics. But there's one bad habit that you get in statics that we have to make sure doesn't carry over to dynamics. And that is that, remember, in statics, when you're dealing with rigid bodies, you can always calculate your moments about any point you want. Okay, remember that? In dynamics, you can't. There are only two possible places you can put your about point for calculating your moments. That about point A is either the center of mass of the rigid body, or a fixed point on the body. And when I say fixed, I'm saying fixed to your inertial coordinate system. Okay, so this is kind of like the bottom line on equations of motion for rigid bodies. And we're going to use this stuff over and over. Like, this is a total key bit of information for this class. Let's think about how many equations and stuff this gives us. So Newton's second law. If you're doing problems in 2D, and often we are going to be doing problems in 2D, Newton's second law gives you two equations. That's the x and y components. And if you're doing problems in 3D, this gives you three equations. And then for the rotational Newton's second law, if you think of motion in a plane, there's only one axis of rotation you can have in a plane. So in 2D, this gives us one equation. And if you're doing it in 3D, you need to have a different approach. And we might be able to get to how to do these in 3D at the end of the class, but for rigid bodies, we're really going to confine stuff to the plane for now. Yep.
Could you get two equations out of the rotational second law by having your fixed point, everything has to equal 0, and your center of mass is able to move around?
I can't quite picture what that is, but you can't. I mean, this is like a mathematical law, and that's just the end of it. It's kind of like, when you first start doing algebra with multiple variables, and you're like, man, maybe if I'm clever enough with my algebra, I can figure out how to make this one equation solve for two variables. I'll do this and this and this. And then later on, you're just like, no, that's just a law, That it's the same with this. So things only move around one axis, so you only get one equation. Okay, so looking at these equations, it brings up a few things we have to define before we can use these. Before we can use these equations, for rigid body motion, we need to define, bless you, three things. First, we need to define the center of mass. Second, we need to define the mass moment of inertia about a point. And I put this stuff in parentheses. We're always going to denote this capital I sub A. I put this stuff in parentheses because you should always have this stuff in your head when you talk about it, but people just call it the moment of inertia, okay? But the reason I put this stuff in parentheses and the reason you should always have it in your head is most of you are going to end up taking D-form at some point. Some of you are taking it now. And coming up soon in D-form, we're going to have a moment of inertia that we call I sub A like this, but it's the area moment of inertia about a centroid, and it means a totally different thing. And so you have to keep those two things straight in your head. Why do they call them the same thing? Because a moment is a mathematical thing, you know? So calling something a moment is really just saying mathematically how you calculate it. But yeah, it's these two things that are very important for mechanical engineers and related fields mean totally different things, even though they look the same. The math is sort of the same, you know, it's kind of a mess. And then the last thing we have to define is, we'll just call it the moment, again, because of the mathematical definition, but you should think of it as the moment of a force about a point and I'm going to call that the vector MA. Okay, so, I mean, this is the most obvious quiz question in the world. When you're calculating a moment, what are the two places that you can choose your about point to be? Okay, and the answer is the center of mass or a fixed point. Okay, you have to keep that in your head as you go through this class. In statics, why did we get to choose the about point anywhere we wanted? That's weird. Yeah, because everything is a fixed point. Exactly. Okay, but in dynamics, only one thing is a fixed point at most. Sometimes, if you have a fixed point, you want to use this one. If you don't, you have to choose the center of mass. So like if you're doing dynamics of a boomerang or a satellite or something, nothing's a fixed point, and so you have to choose the center of mass as the about point for everything. Okay, so we're going to start with the center of mass, defining that. And the first thing I'm going to do is kind of adjust the calculation of center of mass to the calculation of a centroid. So if a body is homogeneous, What does homogeneous mean? The same throughout, so no chunks of other stuff in it. Chocolate chip cookies are non-homogeneous. You know, what? Yeah, if you mix it carefully. But yeah, so like when you homogenize milk, you like mix it all up, you know? Because there's like, it starts with like rat poop in it and fur and whatever. You just stir it all up so that stuff is all. Okay, so if the body is homogeneous, then the center of mass is the centroid. And so what we're really going to calculate is the centroid. And so the integral definition of the centroid if you're doing 2D problems, which like I said, we're going to be doing mostly 2D problems, x bar, y bar, the coordinates of the centroid, are 1 over the total area times the integral over the total area of xy times dA. And this xy is the centroid of your infinitesimal area dA. If you're in 3D, you're dealing with volumes instead of areas, but otherwise it looks pretty much the same. Your centroid coordinates are 1 over the total volume times the integral over the volume of x, y, z dv. And again, like you would imagine, this is the centroid of your infinitesimal volume dv. Okay, so there are 3 things. Okay, so this wouldn't be great. I mean, if every problem we did, we had to calculate this integral, that would not be ideal. But 3 things come together so that we don't have to use these almost ever. So these 3 things conspire. So you usually don't have to use the integral definitions. So let me write them out and then I'll go into them. So the first one is the centroid always lies on lines or planes of symmetry. Second, Which did I do second? There is a parallel axis theorem. Let me do that one as third. So second is, once you do the integral for a shape, you can just use the formula, the algebraic formula. So basically, like, all of humanity only has to use the integral definition one single time for each shape, and then people can just use the formula that they come up with. Third is the sum formula, which says if you can break a complicated body up into simple shapes, and you know the centroids of those simple shapes, you can just use this simple formula to come up with the centroid of the complicated thing. And then fourth is the parallel axis theorem. Parallel axis, no. I'm sorry, that's wrong. I didn't have that in my notes. I got confused for a second. So these are the three. Yeah, three things conspire. Okay, so if you can find lines or planes of symmetry, you can simplify the process. If somebody's already done this integral formula, you can use their algebraic formula, and then you can break the body up into individual pieces and use that to calculate the centroid of the whole thing. So, okay, the first one is that the centroid always lies on lines or planes of symmetry. So for example, if you have, so let's say like the Star Trek communicator symbol. Okay. That has a line of symmetry like this. And so we don't know where along that dotted line the centroid is, but we know it's along that dotted line somewhere. And so we've already reduced this from a problem of figuring out two, coordinates of the centroid to just a single coordinate. Okay. In cases where you can find two lines of symmetry, so what about this? This has a line of symmetry this way, and it also has a line of symmetry this way. The centroid has to lie on both of those two lines, which means that it's at the intersection of those two lines, and so the centroid has to be here. Okay. And what about a circle? Well, that has infinitely many lines of symmetry. So at first that might seem like a problem, except that all of these lines of symmetry meet at the same point. And so the intersection of all of those lines of symmetry, again, is the centroid. So for like a rectangle or a circle, you don't have to calculate anything. You just know exactly where the centroid is right from the start. Okay. What about planes? Well, we're doing So this would be like a 2D case. In 3D, which we're not going to spend a lot of time on in this class, you have to deal with planes of symmetry, and it's kind of hard to draw, but you have, one plane of symmetry that goes like this. Like a mohawk. And then you have one plane of symmetry that goes like this, like a mustache. And then you have one plane of symmetry that goes like this. And those three planes, each pair of planes meet at a line, and then those two lines, or those three lines, meet at a single point right in the center. Okay, so the intersection of these three planes is a point, and that's the centroid. Okay, second, once you do that integral formula once for a shape, you come up with a formula, and then you can just use that formula from then on. So here are the centroid formulas that you're going to need for this class. So somebody smart a long time ago did the integral formula, went through it, and calculated these things for you. So centroid formulas. For common shapes. So the first one is a quarter circle. And I'm going to list for each one of these the x centroid, the y centroid, and the area. So the first one is a quarter circle. Okay. And this has a radius of r. The centroid, well, you can see there's a line of symmetry here, so you know it has to be along this line of symmetry, and let's say it's somewhere like this. And the distance from the corner to the centroid is going to be my x bar, and from the corner to the centroid up is going to be my y bar. You can tell from the axis of symmetry that x bar and y bar are going to be the same. And so x bar is 4r over 3 pi. Y bar is 4r over 3 pi. And the area is pi r squared over 4. Then for a right triangle, I'm going to call this distance B for base, and this H for height. And the centroid is here. Okay, so this is what I'm going to call X bar. And this is what I'm going to call Y bar. There's no axis of symmetry on this if you just have general B and H. So these two values are not going to be the same. X bar is B over 3. Y bar is H over 3. And the area is BH over 2.
Those are both from the 90-degree angle, right?
That's right. Yep. Okay, the third one, let's see, how many more do we need? No, this is good. Okay, so for rectangles, circles, spheres, we don't need formulas for those because we know the centroid is right in the middle. Okay. And then the last fact that we need is that there's a sum formula. So if you can build up a complicated shape from simple shapes, and you know the centroids of the simple shapes, you can use this sum formula to get the centroid of the whole thing. So the sum formula says in 2D, X bar, Y bar for the whole shape is equal to 1 over the total area times the sum for I equals 1 to n of the area of the ith shape times the centroid location of the ith shape. And for 3D, you have X bar, Y bar, Z bar is equal to 1 over the total volume times the sum from I equals 1 to n of the volume of the ith shape times the centroid of the ith shape. And one thing to notice is that this is like a finite version of the integral definition. If you look at, or you could think of the integral definition as like a infinitesimalized version of this. Everything is in the same spot. So that's a way to remember these two things, to sort of store them in one space in memory. Also, one thing to notice about these formulas is you can use these with subtracting, let's say subtracting shapes. By calling the removed area negative. Okay, so let me do a simple example with two shapes. How much time do we have? So let's calculate the centroid of this thing. We'll say that the total length is 4 meters. The total width is 2 meters. This is 1 meter, and this is 2 meters. And let's put our coordinate system here. So we want to calculate the coordinates of the centroid in that red coordinate system. Okay, and I'm going to do it two ways. The first way, the one we'll do right now, is we're going to break it up into two rectangles that we add. Okay, so I'm going to break it up into, so method 1, I'm going to break it up into this square and this rectangle. I'll call this shape 1 and this shape 2. Okay. For shape 1, the centroid of that shape is, so this shape 1 is just a rectangle. The x location of the centroid, since the whole thing has a width of 1, is just minus 0.5. The height is, since it has a height of 2, is just positive 1. And the area of that shape is 2. Are you with me on that? It doesn't matter if you're with me, I have to go. So then x2 bar, y2 bar. The centroid of that for x is negative 1. For y is, from the bottom of that square, it's 1, but you have to go up 2 to get to that bottom of the square. So this is 3. And the area is 4. And so now we can put it into the sum formula. The total area is 2 plus 4, so we have 1 over 6 times the area of the first piece times its centroid plus the area of the second piece times its centroid And we get, so that's 1/6 times -1, +2, plus -4, +12. And so that is -5, +14. So -5, 6, +14, 6. So what's that? -0.83 repeating, +2.3 repeating.
That's just in meters.
Yeah, I didn't give units, but oh yeah, I did. It's in meters, correct. Okay, any questions? So I'll do it next time. I'll start out next time by doing it by subtraction.
You want to see it brought all the way to decimal, or?
I don't care. Either one's fine, yeah.